then we start looking at the transport aspects with IBEC next. So if you agree, let me know. And in case we can proceed with Tatiana, if you can share your screen, we can review the model and discuss it together.
Sure, I would like to, but I need this co-organizer rights, which I don't have. Genevieve, can you?
Sorry, it's already provided. Thank you.
So after I sent you the model, I added something, and I again have a unit problem at the moment. So just a second, maybe you can help, because this is something between year and month, and this is related to precipitation. So what I did, I added 2 slides. One is related to glaciers and our hydro capacity here, and here I have the unit problem. So this is new. Here basically we have a structure of our hydro sector, and I wanted to add that because I wanted to connect the hydro sector with precipitation and climate. And I was thinking how to do this. This is basically our total installed electric capacity, and I have split it into parts that are depending on different hydro resources. So we have our Atbashi hydro, which is like 40 megawatt, and at Atbashi River. So we can look at the runoff of this river and whether it's fed with the glacier or rain. Basically, most of our rivers are fed mostly with glacier water, about 80% as far as I understand. Is my sound okay? Because I'm with a headset today. Can you hear me well?
Yes, loud and clear, yes.
Okay, so so we can look at the river and the glaciers, I thought, to see how it depends on climate. So that's why I wanted to connect each station with the river that it was actually installed on. So we have this 40 megawatt, relatively small capacity on Atbashi, and then most of it, we have some small hydro and small rivers. I was not focusing on them so far. On Chui River, we have about 38 megawatts, and here we have the largest installed capacity. It's like over 2,000 gigawatt, well, 2 gigawatts, something even more. And these are thermal stations that we have in 2 cities, Bishkek and Osh. They also do electricity generation, but we'll talk about them a bit later. So the main point here, we have our installed capacity on Narin River, and some of the stations are planned. Kambarata 2, for example, is the closest in planning to be built, is also on Narin River. So we are very much dependent for our hydroelectricity resources on Narin River. And then we are dependent, of course, on, because these are all dam hydros. This is a cascade which comes, so there are like several dam hydro that come one after another. And so once you collect in the first dam enough water, then you can actually have electricity from that water, and then you can use this water again on the station that is down the river, and then again and again and again. So here I have total large dam capacity, which is basically Atbashi and Narin River, and Atbashi is actually, it goes to Narin River eventually, so that's why I have them here. And I have electricity produced by large hydro, megawatt hours, and I have it dependent on how many hours it's working per day, which is 24. I have it dependent on loading factor, which I put about 60%, as far as I understand this is correct for us. And here I have something that I wanted to show. The dynamic I wanted to show is that this Toktogol Dam, this is the first dam where we collect the water from Narin River. Its dead capacity is 4.5 billion cubic meters. And maximum capacity is 19.5 million cubic meters of water. So we have to be in between those. I put the minimum and maximum here, and I've put here. So if we have the volume in this dam below the minimum working dam value, then we cannot actually produce any electricity. If we have this water volume more than maximum, we are going to produce a large hydro load factor multiplied by capacity, multiplied by hours working per day. If it's more, did I miss something here? I think I did. If it's more,
no, the equation seems fine. So you have the minimum and maximum.
Yeah.
And so if you put
then
the
we
comma,
have the maximum production. Yeah.
Right.
So
if you put a comma at the end, if it's between the two, if it's not less than the minimum or more than the maximum, then you have the
I have the
hydroload
comma
factor.
here.
Exactly. Yes.
Yeah, I just read the equation a bit wrong. So if it's more than maximum, we cannot produce more than maximum anyway. So we're going to produce the maximum. So this said, we are now depending on the water volume that is in Tokyo Dam. And this depends on two factors. 80%, shall we say, comes from melting of Abramova Glacier, and 80% comes from the rivers. So I wanted to show that. And here I have our Abramova Glacier, which is running off to the through Narin River here to the dam. And here I wanted to show that it depends both on melting of the glacier and on the rivers, and the runoff of glacier depends on the temperature. Here is just I haven't connected it to anything of temperature. It's just it's random. Yeah, I just put it here because I don't know how to connect it yet. And here, so basically, this equation is something like this: 80% depends on the glacier. So we have the glacier capacity by runoff coefficient, depending on temperature, multiplied by 80%, plus 20% depending on the river, which is Narin River basin area, multiplied by precipitation, which is actually per month in our case, multiplied by conversion factor of millimeters to liter, and multiplied by conversion liter to cubic meter conversion, and then converted to billion cubic meters as well. But I still have the problem here with units because you have this glacier runoff per year and billion cubic meters per year. And here, the rivers, I have billion cubic meters per month. So I'm stuck here at the moment.
Okay. Do we have questions from any of the participants? Because I've seen the model and I have a few questions. But before we discuss it in detail, I want to know if others have any concern or have questions about something that is not clear. No questions? Okay, then I'll get started, and then in case questions come up, please interrupt anytime. So the first question is about the production of electricity. Then we go to the units later. Mm-hmm. In the formulation you have either full production or nothing, basically.
No.
So when anytime you have more than the minimum value, you produce at the maximum value, more or less, right? But if you look at
but it's wrong. Yeah, I'm sorry. So
no, I'm just
change those.
No, that is fine in principle. So I'm just wondering if the water is like 50% of the maximum value. Let's say that it's more than enough, so it's more than the minimum, but it's not the maximum, let's say. Production will always be constant, or you have a linear function to say you produce 0 when you're below the minimum, and then you progressively increase output as you reach the maximum. How does it work?
Good question. I think they can work at some level of capacity, and that depends on the demand. They can switch off. We have I think 4 turbines. So they are not always working at the maximum capacity for sure.
And so they're not working at maximum capacity even if there is water, right? Yeah. Because of demand. But when there is water, they need the minimum amount to start working. I mean, there is enough flow to work at full capacity potentially, or the minimum amount is really the bare minimum that allows you to produce something, but not what you would want to get.
4.5 is dead end. You cannot produce anything.
And so at 5 or 6?
At 5 you can.
But you're producing your full load factor, or you're producing less?
You can produce, I think, anything. You can switch on and off one of the 4 turbines and generators. They're like sets of turbines with generators. So you can, I think, go by 1/4, then half, 3/4, and full capacity.
Okay. So this, in a way, indicates that it's not a yes or no. It's not no production or full production. There is the possibility to adjust based on the actual water volume and demand.
Yes, there is, yes.
So one way to incorporate the water volume component would be to calculate a ratio between your minimum, maximum, and the water you have, meaning what percentage of the value that you have in between the minimum and maximum is in the dam. if you have that ratio that goes from 0 to 1, then you can linearly increase production with the threshold you want, right?
But that's not enough. Yeah, that's not enough because we are not always producing again at the full capacity. It's like even if we're at 10, we are not going to put all 4 of our turbines and generators at once because maybe we're in the summer and we don't have that much energy. And we actually have a plan. The government plans every year. Let me show you. They do have a plan where they say how much electricity they plan to produce. How do you get this thing down? Here. So this is an example. So what they do, they plan for each month how much you have to produce of electricity. This is actually demand. This is not an Oblast. Just a second. I'll do this for Kyrgyzstan. So this is consumption, let's say, not demand, consumption, plant consumption. Just to show that we have a planned amount, or we need some amount each month. So we don't actually. I think we have to connect something with this, if I don't know how. But...
No, so basically I would say everything you've done is fine, meaning that you look at the supply side, right? Then there are 2 things that we could do if needed. One, we could improve on the supply side calculation by having that water quantity relationship built in more explicitly with the ratio I mentioned before. But then you may include another component that is demand, so that your electricity produced by large hydro is the minimum between demand and what you could potentially produce. And what you could potentially produce is the equation you have now, is the long equation you have now. So
let's
demand,
have both. Yeah.
So the one way is to do that with the mean function. The other way will be that the load factor changes based on your demand, right? When demand is low, the load factor is low. But I normally prefer to keep the load factor being the technology-based load factor, so it's a constant factor, and then use the mean function to show that the utilization of the plant, or the hydropower plant in this case, declines when demand is low. Okay, but before we add demand, let's continue to review the other parts so that we see everything that we need to update.
Okay, so then this would basically reach to precipitation, and then it would eventually depend on climate here. So this is what I wanted to do. Then the second part, I added thermal capacity.
No, wait. Let's stay here.
Oh.
Can I see the graph for the water volume in the dam to see if it's similar or different to the version I have?
Here's the oh, Jesus Christ. The historical is okay, but this is something. That's a bit too much.
So it sounds like you're going to get a bit more water than you think, right?
Either I'm not. There should be a runoff then, obviously.
Right, there should be an outflow because this is you're not actually accumulating the water. It goes through and it flows out of the reservoir. So you should add an outflow to make so that you indicate how long the water stays on average in the dam. If it has a residence time of 2 days or a month, and so that you can show the stock and flow accumulation.
How do I add that? I mean, I know how to add outflow, but...
Is this a run of the river or is it a full big reservoir dam?
It's a huge reservoir dam.
Okay.
And there are several other hydro below. So it goes from one to the other, to the other, to the other, and then it flows back to the river and to Uzbekistan.
Okay, so I would say that in this case, one option is to say that the outflow is a delayed function of the inflow, or meaning this shows that potentially everything that goes in will go out after a certain amount of time. Or it could be done differently to say that the outflow is a percentage of the stock, meaning that if you have little water, nothing goes out until you have filled up the reservoir up to a certain point, okay? But of course, when the reservoir is full, then the behavior will be more or less the same. So what do you think would be the best approach in this case?
I think it would depend on how much the water is there in the reservoir, but not, it will depend on the amount of water basically and on demand as well. It depends on 2 things. Sometimes we just let the water out when it's spring, because it's spring.
because you don't need it for generation, and there is a lot
we
coming.
do need it for generation, but we have our agreements with Uzbekistan and
Okay.
the water anyway because it's spring for irrigation.
So it sounds like the water inflow is the main determinant in this case. Based on the season, you would have a higher or a lower percentage of the water inflow going out, right? Or let through, basically.
We are accumulating it in during the late autumn and winter. Late autumn, I would say. In winter, we have to use it for energy because our electricity consumption jumps threefold in winter compared to the summer. So we do have here the graph, for example. Here we have, let's say, this is the inflow. The green one is the inflow, and the red one is the outflow. These are the 3 months, but we can actually, this is starting from June 19th. You see here, and when we come to the winter, we have the outflow more than inflow, and then back again. At about, let's say, March, right? Here is some kind of gap in data, but anyway. So this is our basic behavior with this. But I think the outflow is pretty much constant at like 300, apart from winter when it is obviously 700.
Okay, so this shows that we cannot only use the inflow, right?
Yeah.
Otherwise, we miss the winter.
Yeah.
Trend.
Yeah.
And if we use the stock, this is a function of the accumulation. Then we can say we use different portions of the stock depending on the season, or we just determine the outflow with an exogenous trend, which is a seasonal trend as well. And exogenous could be endogenized by looking at the required electricity generation during the winter, determining the amount of water flow that you need to produce that amount of electricity.
Yeah, I think it would be right if it would depend on our needs, actually.
Okay.
We can even a function, maybe monthly average.
We can introduce monthly values, yes. So I think one aspect first is to convert a cubic meter of water into kilowatt hours. So you can say, I have a demand of a certain amount of kilowatt hours or megawatt hours. How much water do I need to produce it? So this would be the demand of water for the large hydropower generation, right? Which could be used as the primary input for the outflow. So you can say, this is the outflow I need for the production I want. And then we manage separately the inflow with the seasonal values for precipitation, so that then we also fix the units.
So water per megawatt, I have no idea how much do we need. I think 1,000, I don't know. This is random. Because it depends on so many factors, and you cannot, I couldn't find information here.
I would just compare the water outflow that you have in the previous graph with the power generation and do a simple ratio and see what range.
Yeah, but I don't have a daily, I don't have a daily generation. This is just happens to be, we're just lucky to have this, but we don't have the generation.
This is a daily value that you have in this graph?
This is a daily, this is the weekly value here. This is the volume of water in...
So cubic meter per week.
Yes. And here, per week we can have this. And this is per day. This is inflow and outflow, but we don't have the production per day.
But if you look at the winter months, you have about
you can have an average.
Exactly. If you have about the same level of production or say outflow per day, do a simple multiplication by 30 to compare it with the monthly generation. You see, this is fairly constant for 3 months, right?
Yeah, pretty much.
Which probably means that you use the dams at full capacity for 3 months.
Yes, I think it does.
So if you have the maximum output that you have in the model, and you have here the 700 cubic meters per day is the water flow, right?
So you think 700 cubic meters equals 1,200.
It's 21,000 cubic meters per month, right? And then if you see what is the maximum generation potential per month, then we compare it.
Potential generation per month, we have, I think it's, let's say, this is Toktagul Dam, this is 1,200, and multiplied by 0.6, that would be multiplied by 24 by 30, right? Do I need to multiply it by 24 hours?
Yes.
2 days, yeah. Okay, 518,000. We have about 0.4 cubic meter per megawatt hour, if I did everything correctly.
Now, are you sure that the unit of measure for the water outflow is cubic meter and not 1,000 or million cubic meters per day?
I think it is cubic meter per day. Yeah, cubic meter per day. Do you think it's not feasible? This half
It
cubic?
seems small.
I think it's. I thought that's cubic meter per megawatt hour.
See, Irina for India says 3.5 cubic meter per megawatt hour generated.
How much?
3.5 cubic meter per megawatt hour. You had a similar number, right? You ended up with 4?
I have 0.04. So I have like half.
0.04 cubic
Yeah.
meter per megawatt hour.
Yeah, but it's really high, the dam. So have you looked at the dam hydro specifically or something else?
No, I've just done a very quick search, quick Google search. Let me see.
Let's have I think 0.4 is okay. It should be okay. We can calculate it again.
As soon as we run it, it's easy to test it. Yes.
The point is that there is the production of hydro is equaling the pressure multiplied by the volume of water that goes through it and multiplied by some coefficient. So it depends both on the quantity of water and how high is it, which height is dropping. And since this is quite a high dam, we might be more efficient.
Okay.
So, but we can check it again later. I think this would be good to do within the model, all these calculations, or not?
Yes, you have to embed it in the same way. Yes. So you need to include in the model the average water consumption per megawatt hour. Then you have the generation already in the model. So you can calculate the total water requirements for hydropower generation. And that becomes the outflow of the stock, of the water volume in the dam.
This is only part of this. This is like, then I have to split the installed capacity on Narin into the 4, because these are all of them. These are like 4 stations. And we only have the first one is 1,200. So I would have to do it differently. So let me see. We have average consumption. Do you say average consumption of?
Average water consumption per megawatt hour of power generation. Yes.
But I have that already. I did add this. We just put it in as a constant. And then how shall I say? I'm not sure if it's needed. This structure. So I mean, this I can connect to the installed capacity on Narin River later, or it's just how shall I do this?
So you want to add it because the water use that we have from the chart you saw before, it's for additional production, right? Not only for what you already have in total large dam capacity.
We're talking now when we have about Toktogul Dam specifically, because there are several dams after this.
Okay.
We have to talk about, when we talk about outflow, we only have to look at the 1,200, not this.
Not the full.
Not the full capacity.
Follow on. Okay.
Or I can just have it as a share, or I don't know. How shall I do this? This is useless.
Well, if you want to look at the total hydropower generation, you need to look at total capacity. But if you say that when there is water at the top, there is water later on as well.
Yeah.
Then make the calculation for that one first. And then you can use an if then else function for the other ones. You can say if there is full production here, then there is full production there. We'll just multiply the generation by the additional capacity you have downstream. And you can also integrate everything in one single stock. And it just happens that you're more efficient, right? Your average water consumed per cubic meter per megawatt hour becomes higher because you have a series of dams along the same river. Either way is fine.
Let's delete this thing and have this. And here we have then megawatts. Okay. What happened?
You can click on the flow, the rate, and okay, either undo or click again in the symbol in the middle, and then the stock connects again. But do check the equation for the stock now, because when that happens, the sign may change.
Yeah, I wanted to add the minus, but it seems that the plus is gone, actually. Water inflow minus water outflow. That should be fine. And so we come to the water outflow. We have, this is billion cubic meters per year. I have to have the demand as well, right? Per year, per month.
So the demand here, if you want to connect it with the electricity demand we have elsewhere in the model, there could be a share of the total electricity demand, which is the portion that is produced by hydropower. And then we can apply the seasonal variations.
Do we have it elsewhere in the model? I don't think we do.
We have total demand at national level, yes. Then we also have total hydropower generation, but this is a subset, and so it's fine to keep it separate. But the variable that is the demand is called, and in this case, we take into account losses as well, right?
Then we'll have to call up.
I think it's called desired electricity generation.
Desired electricity generation. Where did you find this one?
It's in the power generation capacity, top left corner. So it takes the demand in terajoule, converted in megawatt hour, adding losses.
This one, demand for electricity, endogenous?
Desired electricity generation, just a little bit to the right, just below from where you are now.
This one.
That is the total, so we can calculate the portion that is from hydropower based on the data that you have.
I have thermal here. I don't want to add. Lines of it.
Now the model doesn't match the historical data because GDP has changed in the last few modifications we made, and so that's why it's a bit off.
I did also add here distribution lines.
Yes.
And I was supposed to add, thermal.
So this is taken into account. So we have demand plus the losses, and this is the generation that is required.
Set electricity generation.
Another option, if you think it's easier, is just to add demand as an external function now, and then we make it endogenous. Once the model is fine, we connect it endogenous, if you like, as you prefer.
Well, I'm just thinking that this is per year, right?
Yes.
Per year, but we need it per month.
So that is an extra variable we need to add. So I can show you where to find it and how to use it. But then let's take it step by step, because now we're adding many things without completing any of those, not fully validated. But if you go to...
Let's do it, desired electricity generation.
Yes, you can bring it there, just so for now it's there.
Then we have share of total electricity. This we can, basically this is 91%, but this also depends on year. We have historical data for this actually. Have it like 91%. 92.
Yes, and of course this value will change seasonally as well, I guess. But let's keep it constant for now.
So then we have this.
Then let's go take the last piece before we connect this, the monthly disaggregation in a way. If you go to precipitation and then look at seasonal distribution of precipitation at the center there, and look at the equation. So this one uses the month
This
counter
is for every
modulo
month you have
as an input. Yes, and then below in the lookup you have for month 1 you have a certain percentage.
See where you would look up dimensionless.
So you can copy this seasonal distribution of precipitation. No, the whole variable, not just the numbers, just the whole variable, and then copy and paste in the sketch we were working on before, the glaciers and electric capacity. When you paste it, you can change the name, and so this will be seasonal distribution of power generation, right? So this is then where you can add the percentage of the annual demand that comes in January, February, March, and so on and so forth from hydropower.
Good question. This is like.
You can also click on as graph if you prefer to change it manually and see it visually. It's the same as a normal lookup function.
Yes. So starting from 11, we are going to have. Let's be very simple about this. Let's say apart from winter 4 months, during the 4 months we have 7. So I'm just doing it out of my head. So 700 multiplied by 4, we have 2080. And then we have other 8 multiplied by 300, basically 2,400. So the total we would have during the year is 5. I'm just doing this. So during the winter, we would have 13% produced. Let's say, let's start from here. 13, just to have it even. Then we can have the correct values, but I think it's pretty much. And then the rest of them would be, so 5.7, not that 0. I'm not sure if it would come to 100. Yeah, something like this. So this is not right. Let's have it here. Yeah, and here we have 13. So something like this.
So this then we can apply to the annual demand, which gives us the demand of electricity per month from hydropower, which will give us the amount of water consumed per month, okay, that we use as an outflow. So we have to add another variable called monthly demand for hydropower generation. And this will be the desired electricity generation multiplied by the seasonal distribution, multiplied by the share of electricity produced by large hydro.
Then we have megawatt hours per month, right?
Yes.
So megawatt hours per month. How much water we need for that?
So the water outflow, what equation do we use for the water outflow?
And we have multiplied this, right? So monthly demand multiplied by average water that we need for this. And that is going to be, was it in billion cubic meters? Per cubic meters. This is multiplied by billion. 400 million, right?
Well, we will test it very soon. It looked like a small number to me before, but we will test it very soon.
I'll just do this 0.4 multiplied by 100, or multiplied by a billion. All right, so then.
Okay, so one thing to check before we run the model is the water inflow from precipitation. That is monthly or annual precipitation?
This is annual. No, I have the unit problem here. You see, this is the problem that we haven't solved, because this I have partly monthly, partly yearly. And
so instead of using precipitation, I would use in this case seasonal precipitation already, which is measured in millimeters per hectare per month. right? Because you have the seasonal demand, so
Yeah.
you can use the seasonal precipitation.
But then I have to redefine the runoff from the glacier as well. I'm not touching precipitation, sorry, because I might delete it.
No, you can select it with the hand tool, then press delete on your keyboard, and then
Okay, this one, right?
wait, it's not. There is a bit of delay on the screen. Yes, remove from this view, but do not change model structure. So you remove it from here, but you keep it in the precipitation sketch.
So
okay, so now
precipitation now, but we have to change it to seasonal runoff coefficient. This is per year. So I have to change this coefficient as well, which I might do because this is just out of my head as well. I might.
And you can use the same formulation we use for the demand, right? We can finish this change, then run the model, just run it. We're looking at one graph, and then we take the break and come back and analyze the results.
Do you have like you set the time every hour, or you're used to having break every hour, so you just know when to do it?
No, I'm thinking of Nurlan mostly. So we try and do every 50 minutes, maximum an hour. I want to take the break. I know otherwise I will get the message from him. Can we take a break, please? So I want to prevent that.
Because I thought, oh, what a wonderful sense of time. You know, it's like.
Oh, no.
So let's delete that one and connect. We'll then change the water inflow. Sorry. The runoff coefficient. We have dimensionless as graph. Yeah, it's pretty much the same. Let's leave it the same. No, we can't.
Of course. No. For now, it's perfectly fine. Yes.
Because
although I
it's
tend
different.
I tend to think it's the mirror of that.
Yeah. It should be the mirror of this one. So I should think that it starts. It starts in March. I would say that this. Let's just have it a different way. We don't have any here, either here, but we will have 13 right about here. I should think something like this. Oh, wait. Here also this. Yes. And then we will have the part 80%. We have the glacier, we have the runoff coefficient per month, we have 20% of precipitation, and we have not precipitation but monthly precipitation now, seasonal precipitation, sorry. And we have not this one, but yes, monthly. So not year, months. Sorry, is it the year or is it a month? I think it's per month. We have the outside per month as well.
All the stock inflow for water is per month now, yes.
Yeah, my favorite thing. Okay, this year we have billion, water inflow billion per month.
So I suggest, let's see, now we have this issue with the units. Let's try and run the model and see if the model runs or it stops. Then we break, and when we come back, we check everything in
It runs. It does run.
Can you show us a graph? There is a bit of delay on my side, so it comes up late. Either the dam volume or the hydropower generation.
Let's see what we have to produce.
So the dam goes a bit negative.
Yes.
So something is off there. Production goes to 0 because the dam goes negative.
The dam goes. Why is it going on? It's so weird.
I have a sense. I don't want to spoil it. I want you to find the solution.
You mean the inflow is too small?
or the outflow is too big.
It's too big, yes.
Certainly the outflow is too big. That I can tell for sure. Look at the water outflow just for a second. Open that graph. Is this aligned with the data you have? 500 trillions cubic meters per month?
No.
This seems a bit too high, right?
Yes, it's a bit too high. So.
Okay. So I suggest let's take a break for 10 or 15 minutes as usual. Then when we come back, we start the debugging. We start fixing the items one by one.
Okay. So I'll stop demonstration. Okay. So where were we? That was too big.
Yes, the outflow is too large.
Mm-hmm.
So I need to figure out what is the problem with the equations there.
Maybe I have an extra zero there. Well, I had the billion. No, it's 9, right? This is billion.
Yes. Now check the equations. So here you're multiplying 0.4 by a billion, so you end up with a large number. In the water outflow from the reservoir, what do? You multiply the average water consumed per square meter per megawatt hour, which is a large number as we've seen now, by the monthly water demand for hydroelectricity, which is also a large number, right? So are you sure you have to use multiplication here?
It's rather than we have monthly demand in megawatt, or do we have minus monthly demand?
So if you have monthly demand for electricity,
yes,
then you have to multiply it by 400 millions, or you have to divide it by 400 millions. What is the unit? You have megawatt hour per month on electricity demand. Multiplied by what unit do you have here?
Megawatt hour over billion cubic meters.
So you have megawatt hour per megawatt hour divided by billion cubic meters, right? So something is off in that equation. It should be monthly demand divided by the water consumed per megawatt hour.
Then
click on check units and see if you get the same type of outcome.
Doesn't say anything. Units okay.
But meaning that the unit is correct. Yes.
Yeah.
If you did it before, it would probably change it and suggest this one. Try and run the model again. Yeah.
And then let's see the water.
Now it's very small.
Yes.
And so if you look at the dam will go up, right? So, but you are going to want to see a number in the range of 500, 700, right?
But you see the dam here is fine. Basically, this is data. This is the historical data we haven't read.
Yes.
7 billion cubic meters. Maybe it's off.
We have to do one thing actually first. We have to simulate the model using a time step, not annual values, actually, so that we can see more the seasonal differences. Otherwise, now we don't see them. So if you go to model settings, and then save results per time step. Now you have to check that box. Then change the simulation name and rerun the model so that we can see both the annual and the monthly results. And let's check again the values. So say here, we don't have a lot of difference.
Yeah, the dam water is fine.
Let's check the outflow now. Okay, here we start seeing the seasonal changes, the peaks in demand, and then the lower value, peaks in the winter, and then the lower values. You can see the peak in the winter for the year 2010. You see it happens right in the middle of the transition from one year to the other. Okay, then let's see the inflow. Okay, so this is the inflow declining over time. Does it make sense? And the inflow declines over time?
It has variations, but it doesn't decline as such. Okay. I mean, it should follow something like this one. So this is it has like 5 years variation. About one of the variations it's about 5 years.
So let's see where that decline is coming from. Clearly, we need to look at seasonal precipitation, right? If seasonal precipitation declines, then we already have an explanation there.
It declines a bit, but not that.
Not too much. Then what are the other factors that we have to look at?
Then we have the runoff from the
runoff coefficient.
Maybe it's too.
But that is the repetition of an annual, monthly or seasonal trend, right?
Yes, but it's not the repetition, but we did it. We changed it, so we have the maximum during summer and minimum during winter. But basically, yes.
So what else do we need to? What else do we need to review? I mean, precipitation is constant. The runoff coefficient, it has that seasonal change, but it doesn't change by 2050. All the other factors are constant, like the conversion, the river basin area. So what else can we look at to find where the decline is coming from? Look at the equation in case for the water inflow.
Glacier is constant. Or is it? Yes, it is. I haven't done anything to it. Runoff coefficient.
But let's check let's check the graph of the glacier.
Oh, you think it's... we should actually top it with precipitation. It goes to minus. Poor thing.
Yes. So something is off here, right? First of all, if this is a glacier, but we are treating it as the water contained in the glacier, right? So when it reaches zero, it basically means the glacier is gone. Right? That's the idea. And then the initial value you see is actually fairly low. You have what, 6 billion cubic meters?
Yes. But this is how, I mean, this is what I estimate that actually is. It's like,
yes,
it's 22 square kilometers, and I multiplied it by 10 to have billion cubic meters, and by 2.5 because it is about 250 meters deep.
Okay. But then what we're looking at here is the fact that it can only decline, so it only flows out. There is no regeneration or reaccumulation of water and ice during the winter. So that
Do we
is
go
one
to seasonal
dynamic.
precipitation again? Can we connect it back to glacier?
Connected to the inflow.
Connected to the inflow to the glacier. This should be over the glacier area, and then we will use this Naren. Where do we have this area? Area is already inside 22 square kilometers. Yeah, probably I should have done this as a separate value.
You could use it as a separate stock and flow for the size of the glacier, but it's also fine to have it as a quantity of water, as long as you're able to match the trend in the stock of the size of the glacier. So now we are only concerned about the trends, right? If the trend is declining from the beginning, it doesn't seem reasonable. It should be more of a slow decline and seasonal. So you should see the shrinking of the glacier during the summer and the growing trend of the glacier in the winter. But over time, the size should decline because of temperature increases, right? I guess that's sort of the goal that you're expecting.
We are now expecting the following behavior. The water runoff from the glacier should increase slightly in the next 50 years, if we're talking about that. But then
then it declines because the size of the glacier becomes smaller.
Declines.
Yes.
Yeah. But we only go up to 2050, so we shouldn't worry about trees too much.
The major changes. And then for the equation, you're doing well. You're extracting the constants that you have in the equation and make them independent variables. Otherwise, you will have problems with the units.
So then we are going to have this connected. And we have seasonal precipitation. And then we already have this one converting to liter per hectare, and then we have conversion of, just a second, we have, and liters to, yes, and we need kilometers, square kilometers to hectare. We do have that somewhere. So then this will be in meters, cubic meters. This one should be billions cubic meters, and this should be in kilometers. Month is fine. Area is kilometers per kilometers. Then we convert. Then we have hectares and seasonal precipitation. Kilometers per kilometers. Yes, of course, I did that wrong.
You may need to divide instead of multiplying some of the variables.
I may, yes. Maybe this is... Okay.
What I do in this case, normally I close this variable, and then I move my mouse over the variables to see what units are actually being used. because I see one potential problem is kilometer and kilometer square.
Yeah. Yes.
So that's one aspect. One aspect that could be.
But this should be
solved.
cancelled. This hectares should cancel the kilometer square.
Because you should have, maybe just by fixing that kilometer square into kilometer, the problem will go away. Try and check what units you use just by going over.
This kilometer to hectare conversion. If we convert it to hectare, then it should be hectare, right?
So this should be kilometer or kilometer square per hectare, or the other way around, hectare per kilometer square.
Be a bit closer, but
so now clearly there is something that is multiplied that should be divided by, right?
Yes, area. Or something divided.
So what is the unit of measure for the area of the glacier?
Square kilometers.
And you want to convert it into hectares, right? At first,
yes.
So you have to multiply by kilometer square, because that is 100 the value you have. So you have to multiply this one. Okay, check the units.
Almost there.
Okay.
1 billion not working.
So
because divided. Maybe.
Tells you that is cubic meter per month, right? So now we know that the land component is fine.
Mm-hmm.
So now we need to start looking at the second part. We need to start looking at seasonal precipitation, liter to cubic meter, and then millimeter to liter per hectare. So I would close this again, and then check the units one by one of the variables that you have connected to
because I connected it to the wrong one, have I? Oh, I need to connect it to this one as well. And how?
So
gone.
That we will fix. So now if you want to have the unit in billions, if you divide by 1 billion, then we know that the unit will be fine.
Do we? Then we have to multiply.
Well, if the unit was cubic meter per month, now it should be billion cubic meter per month.
It's like this. Yeah. So here, finally, units are fine. No?
Something still seems off.
Billion cubic meters per month.
Okay. Yes. No. It was there was a delay.
Should be fine now. This one also billion cubic meters per month should be fine. Why is it not?
Okay. What you can do now to connect them?
Mm-hmm.
If you click on the rate, the flow tool, click once on the stock, the glacier, and then once on the symbol there in between. Yes, it's a bit slow. I cannot. Okay, it did work. Then check the equations both for the glacier and the dam.
So, glacier is precipitation over, fine, and the outflow water in is also fine. Yes, should be okay. Why it doesn't like it?
So one of the aspects is that when you do the integration, the integration is done based on the time step that you are considering. So in this case, the integration would normally be done per year, but we have month added in. So one option to solve this would be to take all the constant factors out of the equation, make them independent variables with their own units, and then the model will be able to understand it better and adjust. But because otherwise it thinks that the transition has to be every year. Instead, you're using month, and so year shows up in the unit just because of that reason, just because the base unit of the model is year. But this is a simple mechanical fix that can be done later on. It's not content related, so the numbers should be okay nevertheless.
So then
here you have another formal problem. You see in desired electricity generation is megawatt per hour, and then in the other cases you have megawatt hours as three letters, M, W, and H. So if you scroll down a little bit to the analysis, you will see that is the inconsistency it finds.
Yeah, it seems I have to change all megawatt hours to megawatt per hour.
Yes. So if you have the explicit calculation when you multiply by the number of hours per day, and then it's megawatt per hour, then yes, then you will need to adjust it. Otherwise, you just include it as megawatt hour with an average generation. But megawatt per hour is good. I think we have it in the rest of the model. I'm just double checking what we have.
We have megawatt
I think
hours.
it's the same. It's megawatt per hour in the other sectors.
Mm-hmm.
Yeah. So I think it's fine to have megawatt per hour here as well.
You mean like multiplied?
Yes.
Then we can, but the number still should be fine, right? So not to
Yes. It's just a format unit problem. So I suggest we go ahead. Yes.
Yeah, and this one also is about the month, I think.
Okay, let's scroll down. Yes, it shows up as the year problem.
And then this one.
Scroll down to see the inconsistency. Well, first of all, you see that you have some numbers in the equation, right? And so it's the model doesn't fully match the right. Technically, every variable should have a unit for the model to be able to calculate well all the units.
Billion cubic meters.
Go down a little bit, just a little.
That's it.
Or it's the bottom.
That's the bottom.
Okay, so the calculation, it says the glacier's runoff coefficient times 0.8 is billion cubic meters, while the variables that you put in the other portion of the equation have billion cubic meter per month. So if you say that the runoff coefficient is not dimensionless, but it's dimensionless per month, because it's runoff coefficient is a monthly coefficient, then the unit in this case will be fine.
Yes, I did that already before, per year, but okay. But it should run fine anyway.
Yes. So we can run the model and see if the numbers are actually okay. The units are not preventing the model from working fine. So if there is any problem now, it will be because of the equations or the numbers.
Okay, the dam volume is actually
same as before.
Same as before, but it cannot be 22.5. So it can only be 19.5.
Okay. So let's start from the top. Look at the variables one by one, because if you start from the middle, you never know whether the problem is at the beginning or at the end.
Okay, precipitation. Ooh.
Right. So this is the monthly value of precipitation. It's a portion of the total that we have that only applies to the specific area, right? And it's in billion cubic meters per month. So here, it's hard to say whether it's right or wrong, the total size. We will need to compare it with data.
But it declines a bit for some reason.
That is the trend of precipitation, right? It follows the trend of precipitation that we have in the model.
Then the glacier, let's see. Oh, again, it's in the minus. Nothing changes here, which is weird.
Well, this shows that the outflow is bigger than the inflow.
Bigger.
So let's see what the outflow looks like and maybe put it together in the same graph with the inflow.
In the same graph like this. Is it? Does it show?
Yes. So what do we see? What is the difference between the two?
So precipitation is pretty much constant compared to water outflow, which is inflow.
So why is the outflow larger than the inflow?
Because we need to use it for energy. So probably we use too much for energy.
No, but the energy comes up after the dam, right? Not from the glacier. The glacier, in this case, it's a natural process. So either we have, in this case, the amount of inflow that is too small for some reason, and that we need to verify, or the amount of the outflow is too high.
Too high.
And so what could drive that? So let's see the two formulations on the right side. You have the precipitation over the glacier, which is affected by precipitation, the area of the glacier. Right? And then we have the inflow from the river into the dam, which is affected instead by the river basing area, the runoff coefficient. These are the only two differences. Then you still have the same seasonal precipitation.
But that in river basin area is huge.
It's larger than the one of the glacier, right? Yes.
Much
so
larger.
That could be one of the reasons. So not all of the water inflow, to the dam comes from the glacier. Some of that comes from precipitation that happens in the river basin area, right?
Yes.
So maybe the numbers you have for the water inflow are right, but they should not all take quantity of water out of the glacier. So what I suggest to do in this case is to create a new inflow to the dam, that is only the portion of precipitation that comes from the river basin, and the inflow that comes from the glacier uses only the area of the glacier.
Yes, and somehow I meant to do that. I did not mean to have it all out of glacier. This is 20% should only be based on river.
Exactly. So you made it correctly in the equation, but then the fact that the flow is connected to the stock, it takes out everything from the stock, right? So you can do copy paste of this equation and only use the component for precipitation, adding it into a new inflow to the dam. But that inflow doesn't reduce any stock, right? It's just an inflow in this case.
Doesn't look very pretty.
That can come at the end. No worries.
It's not an river dam inflow. It's like, let's say precipitation inflow, because this would be...
It could be precipitation inflow from the river basin.
Because it all will come to Narin River before coming to the dam anyway. And then we're going to have here portion only. Yes, and this is going to be 1 billion cubic meters per month, hopefully. This is hard. Let's change this one now. We're going to delete this one from here.
Okay, so let's see what happens now.
Oh, there's errors. Precipitation inflow from river. So Toktagul Dam River, incomplete equation.
You need to add the flow.
Yes, sure.
Yeah.
For sure.
The inflow from the glacier to the dam.
It's funny it didn't light up. Normally it lights up in black when you have to change it.
Yeah, it was black on my screen for a while, but there are a few seconds of delay, so I'm not sure. It was in fact right. Okay, let's run the model.
So let's hope this is going to be fine. Okay, precipitation over the glacier is still the same. Glacier, it's better now, right? Yes, at least it's not.
Yes.
Goes to 0, but not quite.
Compare again the inflow and the outflow in the same graph.
3, right?
It's okay to have the first two only at first. Otherwise, it gets a bit more confusing. So we're just looking at the glacier situation. Okay, so now we have...
Precipitation is still pretty much the same.
The water inflow is the same, constant. The water outflow is still higher. Now, it changes a lot with the seasons, right? That's the runoff coefficient that changes, I guess, that gives it the seasonal trend. And we are taking here 80% of the water, right? And then we apply the runoff coefficient. So either we need to take less than 80% to take it down. So you basically, with 80%, you're saying that you're losing 80% of the water every year, right? And then it reaccumulates, correct?
I want to say, let me just rename this thing because this is not right. This is water inflow from, say, Narin River, from last year.
Yes.
I don't know whether this is clearer. 80%. The point of 80% was to show that this, I don't need this 0.8% actually, do I?
Right, because if you multiply the stock by 80%, you're saying that you take 80% of the stock out. You're not saying that you take 80% of the water inflow coming from the glacier. So if you have now the runoff coefficient and the glacier, the output that you get from the model, you need to verify for calibration purposes, that is 80% of the total amount of water that flows into the stock.
So then I'll take the 0.2 here out as well.
Yes. Let's run again and see what we get.
So we have the incoming really small and the outgoing getting smaller and smaller.
What is the runoff coefficient?
Where is it? Yes, this one.
Yes. What number do you have there?
Good question.
Now remember, this is the one that
this
adds
is the
up
part.
To, it adds up to 100%, right? So what you need to do in this case is to look at historically, what is the percent of contraction of the glacier during the summer?
Yeah.
If the glacier becomes 30% smaller, you need to apply the 30% share, and 100% of that 30% happens throughout the year, right?
Where do I put it? Or do I have a different variable?
It will be an extra variable, yes. It will be an average contraction. You know, this could be driven by temperature, We have the absolute change in temperature in the model. At some point, we may want to link it. But for now, I would say use a constant factor.
Let's say share of glacier mass summer. I think that would be, if we have this one over the total mass, so let's say we have in the summer it contracts, but I don't think it contracts by over than 20%, if I'm not mistaken.
Well, you can apply the 20% for now, just as an assumption. Keep in mind that if you want the numbers to match, assuming that the inflow is correct, the outflow being 0.6 or 0.8 needs to be reduced by a large factor, right? If it goes to 0.016, then it gets a lot closer to the precipitation. So it seems definitely more reasonable.
I don't know. Let's put 60%. And then we connect it to the water inflow. Multiply it. Then we look at the both of them again. Doesn't change much.
Yes, we had a reduction from 0.8 to 0.4.
5, yeah. It's just weird, it's such a large number.
What is the adjustment factor that you're using now again?
This one is 0.6. Maybe, well, let's use the bigger.
The share of summer glacier mass that you have at the moment, use, let's say 0.1. Because if you multiply by 0.6, you're not taking the difference between the two. You're taking 60% of the change. So if you're using 0.1, you're saying that only 10% is lost, and so you apply 10% to the volume of water. So this, I think, would be more realistic. Because if you say you have a 60%, you have to calculate the difference. It's a 40% difference between 100% and 60.
But still bigger.
Yes. But if we have this as being set, now it may seem like maybe precipitation is too low.
Low, yeah.
So this gives us an idea that maybe precipitation should be higher because it's very, very low now.
The point is that we are taking average precipitation here. I'm not quite sure if over that area in particular we have a larger precipitation, but even if we have a larger precipitation, it cannot be like 100 times.
It seems that exactly it's an order of magnitude or two different, so it is something else. Now for the glacier, I guess it's not only temperature that makes a difference, right? It's not only precipitation that makes a difference. It could be temperature, it could be a number of other factors, right? But at least what you see now is that it's clouds forming and humidity that then becomes ice and so on. But in a way, what you see now is already a more reasonable trend that we can use for calibration. So at least now it's a slow decline and it doesn't go negative. So I suggest we proceed for 5 more minutes to see the other variables and then we take another break again. But let's see, having sort of fixed that for now, what happens to the other inflow, how big it is compared to the one that we have from the glacier, and then what is the total dam volume?
How big this one? This precipitation from... but why doesn't it show there?
So this is 2.5, right? Compared to the 0.06 that we have now from the glacier.
This 2.5, we have 0.01.
Well, 0.01 in the inflow, but 0.06 in the outflow, right?
Yes. So with the 2.5, it should be okay, right?
Well, you said that 80% of the water comes from the glacier, right?
Yeah.
So this one should be 80% of the other inflow. Instead, it is 4 times as big. Yes. So again, that gives us another idea for calibration. So the values that you were putting in, the 80% and 20%, we use them now for validation to determine what is the right value. So if you know that precipitation inflow from the river basin is calculated properly, because you have the seasonal precipitation, you have the area that is relatively clear, right? It's known. And then it's only conversions. Then it may seem that the amount of precipitation is definitely way too low. And then also the water inflow has to increase. The water inflow from the glacier has to increase. Now let's go ahead and look at the next ones. What is the dam water volume? What does it look like?
But this is the stock which is either it can be influenced.
Accumulating in the dam. Right?
Yeah.
Okay. Then let's go ahead and look at what is the water outflow. What value do we have there, the graph?
Oh, this is way too small.
Mm-hmm. So this is very small now, but one thing that it tells us is that maybe the precipitation from the river basin is too high anyway, because this number is it comparable, somewhat comparable to what we have in the inflow? Try and put together this water outflow with the inflow from the glacier.
Yeah, at least in one order.
Okay. Try and compare now the water outflow from the reservoir with the precipitation inflow to the glacier.
Outflow with precipitation.
With the precipitation inflow into the glacier.
Yes, that's what I'm doing. It cannot even be seen.
What you're looking at now is the precipitation from the river basin, not into the glacier.
Glacier. Sorry, glacier. And
again, I'm checking all of them for consistency, right, to see consistency. Okay, so now we see that we are taking out more than precipitation, right? So once again, if we think that the outflow for power generation is right, and we can check these equations, then we have to increase at least a little bit the inflow of precipitation into the glacier, right?
So weird. Why is it not right?
Well, I would look at both the numbers and the equations. Take some time to make sure that the stock and flow structure works fine, and we check carefully every equation to make sure that they're properly calculated, multiplications and conversions are fine, just to make sure that we know which one of the flow is off, whether precipitation at the beginning is too small, or whether the inflow from the basin is too high, or whether the outflow from the dam is too low.
Maybe even the area of the brown. Does it sound like this is right? 22 square kilometers?
May well be.
Maybe it's even larger. Maybe I misunderstood the number.
But what I would do is to look for specific
all these numbers
data.
are found in very different publications. So
that
I
is
don't
normal.
know what they mean by
that is normal. But you need to start checking for data, for numbers that help you validate every single flow. For instance, if you go to the water flow graph that you showed before, are we reproducing the same trends for the precipitation and the water use, the water inflow and the water outflow of the dam?
Inflow and outflow.
Well, now we have it in billions, but in the other graph, the graph that you showed before from the website, it was quite different, right? So we have to compare these two with the website that you had before.
This one.
Yes.
I see. So I mean from there.
So we have to check every key variable against the data. That's the task. So I propose that we take a break now.
Yeah.
Then we decide how to proceed. Meaning that this is something we could start doing together, or you could do before next week. And at the same time, we start with the transport component from IBEC, or we decide to continue with this one, and next week we only do transport maybe. But let's take the break and then we can discuss together.
Итак, согласно нашей программе, от стандартных транспортных средств до экологичных транспортных средств. В основном на
policy instruments like tax or tax incentives to use more electronic cars. And in this slide, I found it absolutely couldn't find any transition to electronic cars. As I understand, you have only actual traditional vehicle stock, right?
Yes, correct.
So here we have vehicle stock and it's mostly traditional, right? So my first step will be to actually split this and add demand for electronic cars, and also add some incentives like the same tax incentive and price for holding these electronic cars, cost, not price but cost. And another thing which I think also will be useful, it's to add not only electronic cars but also natural gas, because currently most of traditional vehicles, they prefer to switch to hybrid vehicle using methane or propane instead of petrol. So I think it will be the first step, which I will add to this vehicle stock slide.
Yes, so the idea would be to add different types of vehicles with different engine so that we can then estimate the energy consumption in a more accurate way, right?
Yes, correct. So here in the first slide, I will add this different types, yes, as you said, different types of vehicles using different, so gas, electricity, and traditional petroleum.
Okay.
I think I can do it by myself. It's not so complicated.
Because
Okay.
this is, at the moment, this is one of the main policies which drives like imports and stuff. I'm not sure about the right-handed and left-handed, because it does have an effect on accidents, obviously. But that's a questionable moment. But at least the engine.
But I'm not sure that I can find the data which will allow us to split vehicles by age, because mostly it's about 10, less than 10 years or more than 10 years. And it's actually only for custom tax, right?
I'm sorry, there is a tax which we pay every year.
Based on age.
On volume.
On volume and on age.
And age, right.
So, and there I think we have like over 15, over 10, I forgot now.
So my suggestion would be, if you think that this is an important factor driving the dynamics of the sector, even in the absence of data for now, I would include it. I would include specific variables in the model for all the new vehicle stock. If no data are available for now, then we just assume that we have an equal distribution, or we only have one type of vehicles, say only new ones, and we calibrate it to make it match with the national data. But if in the future it turns out that you have more data or there is interest for a specific policy, then the model is already set up to add the data or carry out that assessment. So even if we don't have data, if you know to add the equations, I would suggest let's add them in any case, so that we have that built in for the future.
Because at the moment, the reason I'm talking about this, first of all, taxes, and second of all, at the moment, the policy seems to be favoring importing old cars, which we actually don't need if we think about emissions. So we have to change the policy then.
Okay, I agree. Okay, then I will add variable which will indicate the age of the vehicle. I think also there is another thing which we also will need. It's volume, I think, of the vehicle.
Volume of the engine?
Yes, sorry. Engine volume, yes, right.
You mean the size of the engine? Meaning if it's a large car or a small car?
Yes.
That would be difficult, I guess, both data-wise and mostly in estimating the trend for demand, right? Because as soon as you disaggregate the types of vehicles, we need to see how they evolve into the future. But if you see a clear trend for buying bigger cars rather than smaller ones, then it's feasible.
At least for last 10 years, there was demand for big cars, which the engine more than 3-4 liters. I will check this. If I will find data, I will add.
I wanted to ask whether you want to introduce the policy to limit the import of huge cars. It's a question.
Yes, because consumption of the gases mostly come from these huge cars, right? Big cars.
Yeah, we have a tendency of actually the bigger the car, the cooler you are. So we have a lot of people actually driving around the city in vehicles with the volume of engine of 8 cubic meters, which eats up to 30 or even more liters per 100 kilometers, which is simply insane.
So I think it will be good if we could do it, add this variable to the model and check how will be if we will use different tax regimes for such kind of cars vehicle. So another thing which I actually wanted to ask Andrea, it's about the infrastructure for electronic types of car, because still there is question how many cars should be electronic cars should be to build one say, electronic station for such type of cars.
So the charging
Because
stations, right?
Yes, charging stations, because I checked the internet available sources but couldn't find any. Because currently in Bishkek, more than 200 or 300 electronic cars.
So the charging stations are tricky because in a way anyone could introduce them at home, and so they could charge on their own. But then if you have them outside, it increases the potential use in kilometers that people drive. I would want to check maybe the density of charging stations per 1,000 people, something like that, or per 1,000 cars, maybe depending on the data we find in other countries, and compare that to the penetration of electric cars, so that you have an idea not on the impact of charging stations on vehicles, but in a way, the average number of charging stations you should have in the country to be aligned with the trends that you see in other countries, so that the charging stations become an enabling factor for the expansion of electric cars.
So one of the indicators is the results of the program. There should be about around 30 charging stations by 2030. And for me, it's how to add this infrastructure to this model.
So the infrastructure should be added, I think, as a stock, so that you have an inflow, at least the new charging stations being added, and the outflow would be when they get out of service. I don't know what is the lifetime, maybe 15 years or so, depending on the technology used. But then you can show this accumulation, calculate the cost, determine the potential consumption and use of electricity from these charging stations. But where I'm skeptical, where I don't know how this could be done, is linking the availability of charging stations to the purchase of cars. So I would start with the target.
Yes, that's the main question, how to link.
So I would start with the target.
Doesn't depend on this.
Right. I would start with the target number of electric cars by 2030 or 2040, and then determine, based on the availability of charging stations in other countries, how many charging stations would be required to provide an effective service in a way. It may turn out that 30 is too little. It may turn out that 30 is too much. I don't know. It seems to be small, on the small side, on the low side. But at least you can get a comparison with other benchmark countries.
I think also, it should be related to, for example, in Kyrgyzstan, it's quite clear. We have several large roads. So we have a road connecting Bishkek to the south, and we have a road connecting Bishkek to Isikul and Talas, right? So these are like Narin also.
The shopping mall doing this as a strategy to attract more consumers, or it could be together with existing gas stations. So they provide the extra service. So you actually go to the same place, but you charge differently. I guess it's based on assumptions, right? We can run several scenarios and test costs and availability. But again, I would not use it as a driver of demand. I would use it as assuming this demand, how much is the capacity we need?
Okay, so let's move on. So next, it's demand for transport. So here, I think the question about public transport, because you already added bus transport and trolleybus transport. And what if I will add here the transport and split that by bus transport to regional or Bishkek and Osh? Will this work for this slide or not?
Well, in a way, you're going to disaggregate the bus transport and trolleybus within the city and long range, right? That is the idea. And so if you want to expand one or the other, like if you have a policy for expanding one and not the other, or expand them in different ways, it makes sense to disaggregate. Then you have here is the demand, that is the need for mobility, basically, right? But then out of that demand, then you can calculate as the number of buses or the infrastructure available. Here you have trips, so you can say we increase the frequency from once a week to 3 times per week. So we multiply this demand by 3, which determines the fact that we drive more kilometers and we have more consumption. and we need to buy more buses, and so we have a capital and operational maintenance cost. So that you can do that disaggregation. And in the same way as cars, you can do it with different engine types, right? Different energy uses.
Add something. I mean, where do we actually think that marshrutkas are buses? We have these small buses, like which are everywhere.
Mini buses.
Yeah, mini buses.
Microbus.
Yeah, microbus. Are we adding them here, or do we think that these are the buses? Because I would actually consider them a very different transport type.
No, the idea of the program is to switch from microbuses to ecobuses, right? On natural gas and electricity.
So you can add them as a separate category. Yeah, if you want to see that change, then yes. Then you can show the transition by adding both as separate categories.
I think we should, because bus is a bus. A bus for me is something good. It's like municipal transport, it's large, etc. But minibus is something else completely, and we should definitely have some policies about them. So we should actually move them to a different category.
Fine with me. Yes, it means more disaggregation, right?
So, but here's the question, because it will work only for Bishkek and Osh, where we have demand for big buses. But in small cities, I'm not sure that there will be such demand. And how we should split this demand? Big cities and small cities, where they have no such demand for big buses and trolleybuses even. Even with trolleybuses, I think only 2 cities have such option, Bishkek and Naryn. I'm not sure about Osh even.
Well, given that this is a national model, you would need to look at the sum of all the demand.
Nothing in Osh? I think it should be an Osh.
Should be, because I checked, there is only option to buy buses for Osh, trolleybuses only for Bishkek. Okay, so Andrea, please.
So given that this is a national model, you should represent the national demand. But then, of course, the national demand is made of the demand for cities and for intra-city transport. So it's up to you to decide. If you have data for cities, to disaggregate that component and have it as a separate variable, or consider it as part of the total. But if there is a policy to only expand public transport, let's say, in the largest urban centers, then the policy will be sized according to the potential expansion in the cities only and not applied to the whole country.
So does it mean that I should introduce new slide, new submodel for this option?
Either a submodel or different variables to show the urban public transport in large cities, so certain types of buses and so on, and then the other types of public transport in smaller areas, smaller cities, or intra-city. So it doesn't have to be a new sub-module necessarily. It could be just a few extra variables in this one.
Okay, I will check this also. So another question about road network. When I check the program, there is no such options, policy options for improvement of road construction and road network. But in model, we have such. Could you please explain how we can use this slide according to the model, with such model according with program?
I'm not understanding your question completely. So you say we have here some of the infrastructure. Like
yes,
roads.
Yes, we have here the road network,
yes.
And we have policy, some policy options.
Right.
But in the program, I couldn't find any options related to road construction or improvement road construction, and there is no such policy measures for road construction. And how we can use this one in order to improve the program?
We have it here mostly for consistency, meaning that if population grows, if the demand for transport grows, then unless you expand the roads, you end up with more congestion, right? And that has a negative impact on the economy. So that is what I think you should analyze is If it turns out that either in the baseline or in the alternative scenario, demand increases, then the message should be, if you want to avoid the negative impacts of congestion, air pollution in the city, and so on, then the road network should be expanded. Or alternative transport means should be considered, like buses, like you mentioned before, more public transport.
Okay, this is one, it's for country level, right?
Country
Not
level,
dependent.
yes.
Yes, it's valley, mountain.
Or in this case, it's just the total.
In
total
general.
Kilometers. Yes, yes.
So from my point of view, I will work on this vehicle stock. We'll make some changes here. And with demand for transport, I will add some variables for public transport. And demand for microbuses also, which will show the transition from one to eco buses, from microbus to big buses and trolley buses.
Okay, that's fine.
And another question, I noticed in your table that you have the following variables related to air pollution, emission from transport, but there is no data. You couldn't find it, right? Or it's not necessary?
Correct. Yes, there was no specific information. But if there is something new now, maybe for specific locations even, like PM 2.5 concentration rather than emissions for certain cities, and then we could use it for calibration.
Because the main result for green transport, it should be decrease in air pollution, right? It's should be the main result. But if you don't have any data, then it will be the problem. I saw in some publications the information about the air pollution, and they have emission divided to several types. I will check and try to add the information. And about energy consumption, also you have no information here.
Yes, not disaggregated. We only have the total transport sector energy consumption. If you go to the vehicle kilometers sketch, then you will find transport energy demand on the right side. So if you go to the Benson model, yes. And then it's the vehicle kilometers sketch. And the transport energy demand fuel, the variable on the right. And select the variable on the right, the transport energy demand fuel, and then the graph. You should be able to see the simulation and the data. So we have the aggregated demand, not the disaggregated demand by fuel.
Okay, clear.
Something that could be calibrated. I mean, the model calculates, or when you add the different types of engines, then we will calculate demand by type of car and energy source. And so there will be the possibility to calibrate.
Okay. And last question. You mentioned that you will add cost and benefit analysis to transport. Where it will be? In demand for transport or vehicle stock? And what kind of cost and benefit analysis?
Right, it depends on what we can add. So the cost could be, if you take a government perspective, it has to be the government investment. But for the transport sector, the cost is the cost of buying a car, the cost of buying a bus. So it's all the money that we spend. We need to create variables for that. So if you have an idea, as you disaggregate the stock of vehicles about the cost of each vehicle type, then we can calculate the total required investment for each of the scenarios we run. Then the benefits would be the avoided cost for energy if you go to electricity, could be the avoided cost of accidents if we stimulate the purchase of new cars. So these are all variables that we have to identify and decide what is relevant and how to add them. We have the example of the model for Kazakhstan that I showed the other time, maybe 2 weeks ago or so, that we could use as a starting point, because many of the data are international in that case as well. Some are national. But then we can see if the model, the formulations are good enough that you think are acceptable, then we could transfer them, do copy paste and transfer them into this model and then adjust the numbers, the multipliers.
Okay.
By the way, while we're on the Kazakhstan model, can I ask, we did receive, ASEL received the actual description from Kazakhstan and the okay to use the model.
Okay, good.
Of the model. So can we? Yeah, I really want to see the buildings because it's connected with thermal energy. And what else did I want to see? I think it was related to agriculture.
Yeah, we have agriculture, agriculture, buildings, coal, and transport. Yes.
Yeah, I don't know.
Do we have Asel is here on the call on the?
Yes, she's here.
Okay. Can you just confirm in the chat, Asel? Yes, send the model.
Да, я
I'm happy to send it. Okay.
Can you confirm? Just say I'm right. Kazakhstan did show the model. We hear you in English channel.
В принципе, они как драфтовые с нами поделились. Майя посодействовала. Майя, как ты думаешь? Мне кажется, что если коллеги поделились, то мы можем, да, расширить? Мне кажется, да. Потому что мы дали знать коллегам из Казахстана, что как раз-таки этот отчет будет полезен нам для процесса моделирования.
Yes, I can hear you.
Поэтому думаю, что можно поделить.
Okay, so I'll share the model now. Okay, so I will share the model now in the chat.
Татьяна
just
и
the
Айбек
model.
уже получили. Ага, Татьяна и Айбек этот репорт получили. Верно, Татьяна?
Yes, we received the report, but I do need the model. Report is great. I want the model.
No, I can send the model now, and I will send it as just the model, not the simulations, so that you can see the structure and not the numbers. If that helps, that will be fine. So let me look for it now.
Yes, I do see it. Thank you.
Okay, good. So you can review it and let me know if you have questions in the next few days. Don't need to wait until next week. But Ayberk, it would be good for you to review it as well. The transport sector has a lot of the details that you have discussed. But of course, I assume there would need to be some adjustments. There is a lot of detail in the transport and building sector. So I suggest not to do copy-paste of big parts of the model until you are 100% sure that you need everything. If you need portions of this, I think it's better to recreate it using this as a starting point, but recreate it in our larger model, just to include what we need, exactly what we need and not the extras. Because if we add more, then we need more data, we need to look for more of this data, we need to do more validation. So I suggest to customize it. I use this one as an example that I just sent, but nevertheless customize the model to your own needs.
I will use it as simple as I can.
Exactly. So
not to be complex.
Exactly. No, it's actually difficult, right? The most difficult thing for a model is to develop something small and meaningful. It's easier to build something big. But that's why I'm saying analyze it carefully, review it, decide what is relevant and what is not, and then create a model that is your own interpretation that works well for Kyivstar.
Yes, and Andrea, another question which I think probably I miss. So we will develop these submodels and make changes to the model. And what about the general model? So we will send our submodels to you and you will incorporate this to general model and run? Or
yes.
What we will do?
Yes.
We will do?
So what I'm doing now is I'm almost done. Probably by the end of the day today, I will have the full model with an indication of the data sources, which is one of the tasks I said I would do for each of the constant or external variables. Then I'm adding, as we go on, the changes that we discussed. So when Tatiana is ready, for instance, with these new modifications for power generation from hydro and then the thermal component for heat, I will integrate them into the bigger model, making sure that the results of the simulations are the same, then there are no mistakes in that integration process. Same with you. If you make modifications to the model, work on your version, make sure that everything is fine or ask questions as needed. You can write me every day. Don't wait until Wednesday, the day before our session. You can write anytime. I can provide feedback. And when you say, I'm happy with this version, I will integrate it into the bigger model. And every time I have a new version of the bigger model, I will send it to you to you and Tatiana, so that every time we start working from the latest version. We can continue doing this until your sectors are ready. Once your sectors are ready and we start doing policy analysis and running scenarios, then we all work with the same model.
Okay.
When you add variables, make sure you add them with a specific color so that it's easy for me to identify what are the changes you made and I can help you more effectively.
Okay, sure. Thank you.
Okay. So I think we are out of time just now. Perfect timing. But we have the tasks for the next few days. So I will go ahead and complete the documentation of the model. It's fully unit consistent. There will be a full documentation of the inputs and the Excel file and the sources where they come from. Then I will send it to you. You can send me anytime updates with questions. And whenever you're ready, I can then integrate the changes, like the new sectors, into the master model and send it back to everyone. And again, we can exchange on a daily basis. And then we meet again next Thursday for the next online session with the whole group. But if you need a call, if you need advices, if you get stuck, contact me anytime. It's not a problem.
Thank you very
So
much.
Ibek, you'll be working on transport. And then Tatiana, you will be working on validating the stocks and flows for water and then the hydropower. And then adjusting the trend and the absolute value for the heat losses. Correct?
Yes. Mm-hmm.
Okay.
Andrea,
any other? Yes.
Yes, just one request from our colleagues Tatiana and Ibek. Copy us, me and Asel, in email exchanges so that we are aware about the progress. Thank you.
Yes, or on the flip side, they can bother you if you're not writing me enough. But yes, it's good. Let's copy everyone so we're all aware of what is happening and how much we're progressing. Okay?